Thank you very much. So let me take the chance to thank the organizers for inviting me here. I'm going to talk about these results for the first time, excluding my PhD defense, which happened a month ago. And this work is based on this preprint on archive, which happened which appeared there actually the same day of my defense as well. Special thanks to Monsieur Chasseng for establishing the connections that brought me here. So let me start. I'm gonna write on iPad so that also people can follow easily through Zoom. Okay. Let me give a brief overview. I'm gonna give some preliminaries. I'm gonna try to make it as accessible as possible for everybody. I'm gonna talk about some finite height generating functions for rooted planar trees. So then I'm going to couple these trees to their own height. So it's going to be some kind of non-local coupling, which I'm going to explain better in a moment. And then there will be a parameter that is involved. Mu is a real parameter. And for these two ranges of this parameter, I'm going to look at the local limits. And then I'm going to look at the properties of these local limits. And the more interesting case is going to be this case where we are going to obtain a different local limit than the local limits of Vienna-Galton-Watson trees. Okay, so everybody gave a definition, so I thought it's a good idea to give a definition what a planar rooted tree is, although everybody knows what it is. It's given by a sequence of ordered finite disjoint sets, which are the vertex sets at height of this index from the root. And this is how I denote the vertex set of a tree. And to these sets, to these finite sets, accompany a sequence of order preserving maps, which we call the parent maps. And the inverse of these maps are going to give the children of the vertices. Okay, let me skip this for now. Let me first embed them onto R2. Once one fixes an orientation and a right-handed coordinate system, we can embed these planar rooted trees in R2. And in that case, two trees are equal if one can be mapped onto the other by an orientation preserving homeomorphism of R2. So this is how they look like. This is my root vertex, and this is my root edge. In this case, D0 and D1 are one-point sets, which means that it is just a convention that the root vertex always has valency 1. I'm going to denote, so I'm going to fix some notation now. Let's say this is the vertex J. I'm going to denote the degree of a vertex by sigma J. And the sectors around J are these things. So if I draw a little circle around this vertex, this circle is divided into two angular sectors around this vertex, and these I'm going to call sectors. So this denotes the vertex around which I'm looking at these sectors, and these are going to be the sectors that are ordered consistently according to the ordering of the children, and there are sigma j of them. So here, this is the valency of this vertex J is 2, and I have two sectors. This is going to be important for the grafting procedure that I'm going to explain in a minute. So the planar rooted trees of volume n, which means number of edges is equal to n, I denote them by Tn. The set of finite trees, I denote them by Tfin. And taking the union with the set of infinite trees, I denote the whole set by T. And BRT is the subgraph of T spanned by the vertices that are at distance at most r from the root. By distance, I mean the graph distance. And then I can put a metric on this space, which will make it a complete and separable metric space. And the metric is defined such that the distance between two trees is the infimum over 1 over r, where r is a natural number such that these subgraphs, they agree. So the two trees agree up until height r. And then the ball of radius 1 over r around a tree in T is defined such that it is the set of all trees that agree with my tree T0 up until height r, basically. Okay, these were all very well known to everybody, I guess. So I'm going to define what a backbone or a spine is. This is going to be important for the second part of the talk. So in every infinite tree, there are two types of vertices, infinite type ones and the finite type ones. The ones with the infinite number of descendants, I call them infinite type vertices. So if we say that, let's say, attached a tree here, grafted a tree here, which has only infinite type vertices, then the backbone of the tree that you see in the picture would be this subtree here. So the backbone of an infinite tree is the subtree that is spanned by infinite type vertices of that tree. And this operation of deleting all finite type vertices together with its descendants is done by a map that I call chi, which turns out to be Borel measurable, and it's a map from T infinity to T infinity. And the image of that map I will denote by Ts, which I will call spine trees, and these trees have only infinite type vertices. And there is one more map that I want to talk about. It is the grafting operation. It comes with a base tree on which I'm gonna graft trees, and a set of vertices. Here there are k of them, and the corresponding sectors onto which I want to graft these trees. So once this base tree and these vertices and the sectors are given, this map is it's a homeomorphism onto the image from T to the K. So this is important because then I can say that if I have a finite tree, any tree in the ball, in this case, in the ball of radius 1/3 around this finite tree T0 can be achieved by grafting k number of trees on the top vertices. So I'm going to talk about local limits, I said. So to talk about local limits, I'm going to construct local limits as the weak limit of a sequence of probability measures. And what a weak limit, I mean, this is what weak convergence means. I guess everybody is familiar with that. But I just want to know a case I just want to note a case specific thing. With the measure that we defined, with the metric that we defined on this space and the balls, it turns out that any ball is both open and closed, and two balls are either disjoint or one is contained into the other, and the set T fin is a countable dense subset of the whole space T. And given this information, it can be obtained by using basic results from the theorems of weak convergence of probability measures, that the convergence of a sequence of probability measures is fully characterized by the convergence of their values on the balls. And this is kind of important because anytime that I'm going to talk about the properties of some limiting measure that I'm going to generate at the end, I'm going to look at their values on the balls, and they are fully characterized on balls, so it's going to be fine. So I said that I want to couple trees to their own height, so it is probably a good idea to talk about generating trees of a certain height. Generating functions of trees that generate the trees of a certain height, or the trees up to a certain height. So xmg, I call them generally finite height partition functions or generating functions. I use them interchangeably. This is the generating function for trees of height at most m, and so this is the number of trees that have n edges and height m. And there is a recursion relation. These things are also written in many places. And x1 g is equal to g. And this recursion relation can be solved explicitly to give this closed form of the generating function. And it can actually also be written as a fraction of two Chebyshev polynomials of second kind up to a factor of square root of g, from which we can analyze fully the singular behavior of these generating functions. They have poles, and all the poles are simple. These are the locations of the poles. K runs from 1 to m/2 floor. And these are the residues that are associated with them. Then I can just write xmg by using partial fractions as a sum over the residues divided by g minus gk. These are determined by some initial conditions where xm0 should be 0 and x prime m0 should be equal to 1. And then I can just Taylor expand and find out these coefficients that were the Taylor coefficients of my generating function. Okay, the explicit form of these coefficients are going to be important again for the second part of the talk. But it is good to keep in mind that there is a sum over the number of, there's a sum over the poles here. K runs from 1 to m over 2 because this is going to be used again. Okay, so I said I want to find the local limit of these objects. So let's remind us the uniform infinite planar tree. If I have a sequence of finite size uniform measures that are supported on Tn's, which I define, they are uniform probability measures, so I just divide 1 by Cn minus 1. Cn minus 1 are the Catalan numbers, and this minus 1 factor is because my convention is that my root vertex always has valency 1. And then I can look if these measures, if these finite size probability measures, they converge weakly to a measure nu that is supported on the set of infinite trees. And I mean, it is well known that this limit exists, and it is called uniform infinite planar tree, and it is such that the limit consists of a single spine tree together with some critical Bieniemy-Galton-Watson trees that are attached on this point. So it's one-ended. This is the thing that we want to keep in mind. So what I ask now is the question, what if I start a different set of finite probability measures which are not uniform? And what if I start with what if I make this different sequence of finite size probability measures weighted by the height of the trees in this way that is written here? So it is actually a very simple idea and a very simple thing to try at first sight. So mu is a real parameter, ht is the height of my tree t, and these are these normalization factors which are given just by the sum of the weights of the trees over all trees of volume n. And I can rewrite these normalization factors in two different ways which will be of use. So remember that I found out, I know the singular behavior of these finite height tree generating functions fully. So then if I want to couple my trees that have exactly height m to their own height, I can find the generating function of trees that have exactly height m by just taking these differences. And then I can multiply them by a factor of e to the minus mu m, where m is the height of the tree, and sum over them and calculate these normalization factors here. And then the normalization factors are going to be the Taylor coefficients of the terms Gn in this case, or I can simply directly sum over the coefficients of the the difference between these coefficients of finite height partition functions. So this is going to be what I'm going to do for mu smaller than 0, and this is what I will need to use for mu greater than 0. Okay, up until now, I think everything has been pretty simple. And let's go back to the question of local limit. I said that I want to show the existence of a local limit as the weak limit of a sequence of finite size height-weighted measures. Okay, but as I tried to say at the beginning, these height couplings are somehow non-local in the sense that the weight that is associated with a tree cannot be written as the product of factors that are associated with the vertices, as in the case of branching processes. So the technique that I want to use is slightly different. I want to use a slightly different algorithm to explore, to show the existence of the local limit. And this is for uniform infinite planar tree. It is done in this paper by Durhus from 2003. It's actually pretty standard method that brings together some theorems and results from the from convergence, weak convergence of probability measures. So I need to do two things. The first step is to show that my sequence of measures is tight, by which I mean that for every epsilon there exists a compact subset of my space such that the mass of the complement of that compact subset is smaller than epsilon for every n. And once I show the tightness, this guarantees the existence of convergent subsequences. Then I just have to show that the limit of the subsequences is unique, independent of the subsequence. Then I have the result of the existence of a limiting probability measure. And by sufficiently many Borel sets here, I mean the set of balls, actually, for the reason that we talked about before. So I just want to emphasize that the set of this T is not compact, but there are compact subsets of it if I choose these KRs sufficiently large, a sequence of positive numbers, sufficiently positive integers such that KR are sufficiently large, then I can actually prove tightness, and I'm going to say how we actually prove it in a moment. I just want to emphasize one thing. Okay, now I have the algorithm, but what do I need to solve the steps of this algorithm? What I need, the first crucial ingredient that I need is the asymptotic form of these normalization factors that I have here, which makes sense, right? Because I want to compute some kind of limit, and I want to understand how these look like for large n. And so how do I do it? There are, of course, multiple ways of doing it, but I think the most generic way is to write down the generating function for these variables. And then try to understand the singular behavior of the generating function, from which I can extract the information of the asymptotic behavior of its Taylor coefficients. And one can use transfer theorems, which are due to Flageolet and his colleagues, I think. And this is going to be the technique that I will use for mu smaller than 0. And so let me move on to the case mu smaller than 0. This case is fairly easy to understand. So I just rewrite e to the minus mu as k, where k is greater than 1. And this is just a notational thing that we use for simplicity. And let me define gck, where c stands actually for the critical point, by k over k plus 1 square. And notice that this is smaller than 1 over 4 for any k that is greater than 1, which means that the critical point is actually going to shift towards 0. And then the main result says that for fixed k, my generating function for these normalization factors whose asymptotic behavior I want to understand is analytic in a disk around 0 of radius b, where b is greater than this critical value here, so, except one point, that is k over k plus 1 square, where the generating function has a simple pole. Okay, once I know the critical behavior of this generating function, now I can easily understand the asymptotic behavior of its Taylor coefficients. Okay, I'm not going to sketch the proof because this only brings together some standard techniques of complex analysis. But if you want to come back to it, we can come back to it. Okay, so this is just the corollary, and we even don't need the transfer theorems. We can just use, again, partial fractions and expand around the poles and get the coefficients directly. And these lower order terms are going to come from the holomorphic part. Okay, so let's recall, now that I have the asymptotic form of my coefficients, let's recall what I needed to do. The algorithm said I need to show tightness, and for tightness I need the asymptotic behavior of these coefficients, and after tightness I need to show the uniqueness of the limit. And this lemma, together with the lemma here, the numbers refer, by the way, to the numbers in the preprint. If one wants to check, I want to add them. Once I have these two lemmas, tightness follows as a corollary in the following way. So what we do is we compute some lower bounds on the ball volumes. And by using these lower bounds, so m is just in n, and k is the number of vertices of my base tree that are at maximal height. And there are these ends here. So what I do is that after computing the lower bound on the ball volumes, I take n goes to infinity limit first, and then m goes to infinity, and then this limit I denote by lambda of t0. And then one can show that for any r, the sum of these lambda t0s over the trees of height that have exactly r, they sum up to 1. Now to show tightness, I can just rewind this process. I can choose n large enough, then m large enough, and I can choose a large enough subset of trees of height exactly r to show tightness, which follows simply as a corollary. And once I have tightness, I need to show the uniqueness of the, because now if I have tightness result, I know that there exists a subsequence that converges weakly to a probability measure on my space T. And to show the uniqueness of that, I again use this result here, which actually says that the ball volumes are exactly given by this lambda T0 here. And once I know explicitly what the ball volumes are, this actually means that the limit is unique because these ball volumes are independent of the subsequence that I choose. So here comes the main theorem in this case, that for each mu smaller than 0, this finite size height-weighted probability measures converge weakly to a probability measure on T. And it is characterized by this equation here. Okay, let's just take 1 minute to look at this equation. Okay, my base tree has k number of vertices at maximal height. So here, in this example, it has 4. It says that this is the generating function x, sorry, I should have written it before, is the generating function of generic trees, of finite planar rooted trees, which is given by 1 minus 1 over square root of 1 over 4g over 2, but it is evaluated at k over k plus 1 squared. So these are, and it is raised to the power k minus 1. So on top of k minus 1 of these maximal vertices, there are going to be finite trees that are generated by this generating function here. And let's say they are these 3. And the one infinite branch is actually going to be distributed according to the same law of the original tree, which we're going to look a bit closer to that in a minute. And this k factor basically says that this infinite branch can be any one of them. Okay, so this doesn't look very different from what we know from the local limits of finite trees, and it actually turns out to be equal to Keston tree. This is just to be complete in what I'm presenting. So I'm looking at the Biennemi-Galton-Watson tree corresponding to a branching process, and I call it subcritical if the average value of offsprings is smaller than 1, and critical if it is equal to 1. And it is a result from 86 by Keston that conditioning, if one conditions on height, one can compute the local limit, which is supported on single spine trees with 2 types of individuals, special ones and the normal ones. The special ones, they span the spine, and the normal ones are the ones that are attached on the spine, and they're going to be distributed independently according to the measure, the Biennemi-Galton-Watson measure, depending on, I mean, either they will be subcritical or critical depending on the branching probabilities that I started with. Okay, so now the result is that the measure that I found for mu smaller than 0 as the weak limit of finite size height-weighted measures is actually the Keston tree with the branching probabilities given as this, and this generates a subcritical branching process. So what I will have is as I just said, but let me repeat, an infinite spine and independently distributed subcritical Vienna-Megalton-Wilson trees that are attached on both sides of the spine. Okay, and this is then the following corollary follows that if I calculate the average value, the expected value of the volume of the balls around the root for the trees, it comes out to be linear in R, which means that the Hausdorff dimension is equal to 1, but this is already known for the Keston tree. And just to be complete again, we know that the Hausdorff dimension of uniform infinite planar tree is equal to 2, and the difference from the case in hand is that in that case, these independent branches are critical. So if the independent branches are subcritical, I have Hausdorff dimension equal to 1. If critical, I have Hausdorff dimension equal to 2. And actually this result is also true almost surely, which is already known for the Keston tree. Okay, and how do I prove this proposition? By simply looking at the values of both measures on the balls, and they turn out to be equal, and we know that every probability measure on every Borel probability measure on my metric space T is fully characterized on balls, so I just conclude that it is Keston tree. Okay, so let's move on to the more interesting case of mu greater than 0. So in the previous case, when mu smaller than 0, these exponential factors were, it was of the form k to the m, where m was the height of a tree. So it was basically, I was favoring the longer trees. I was giving higher weight to the longer trees, and I was telling them to grow longer and longer. And at the end, they chose to grow very narrow and very long, which is shown by the Hausdorff dimension being equal to 1. Now I'm going to suppress them. And suppressing them turns out to give a different local limit than uniform infinite planar tree again. And I'm going to do the same thing. I'm going to use the same algorithm, which means that I have to show tightness, and then I have to show the uniqueness of the local limit. But for the tightness, remember that I needed the asymptotic behavior of these Taylor coefficients, of these normalization factors, z and nus. Now I'm not going to write the generating function for this z and nus. We tried, I couldn't work it out. So what we do is remember that there was one more expression to compute z and mus. We are going to compute them directly by using the coefficients of these finite height generating function for planar trees. And this we do by using a saddle point approximation. And remember that I know the explicit forms of these AMNs, and I said that remember this sum over the poles. So when I now sketch the proof, this is going to be nice to remember. I just want to draw your attention to one thing in this result. I said that we're going to do it through a saddle point approximation, and this says that the saddle point is around the trees that have height around n to the 1/3. This already gives a clue about the change of the local limit, because we know that for the generic case, the average height of the finite trees is given by square root of n, whereas here we have n to the 1/3. So, we are suppressing them, and it is kind of expected. They tend to get shorter. And these A and B are just constant that only depend on mu. Okay, so how do we prove this? We just first rewrite z and mu in terms of some easier, we just simplify the expression. This is basic algebra. This is going to give subdominant terms. And this is the term whose asymptotic behavior I'm going to compute. It is given by a sum over these coefficients of the finite height generating functions. And remember that these AMNs, maybe it's good to look at them actually. Sorry. There was this sum here, so I'm going to look at the contribution from AMNs that comes only from k is equal to 1 part of these AMNs, and that is going to be actually that is the term that comes from the dominant pole, the pole that is closest to 0. And the rest of the terms are going to also contribute subdominant terms to the z and mu. So what we do, sorry for going back and forth, is we consider first contribution by retaining only the first term in AMN, and we define this omega tilde mu to be the contribution from the first terms. This Fn n plus 1 is given by this expression here. And then I'm going to look at around the unique minimum of this function, which is given by 2 pi square n over mu to the 1/3. So this is where the 1/3 comes into play. And an order n to the minus 1 over 3 term. Then to apply a saddle point approximation, I'm going to estimate this W tilde n's in the range around T0, where n plus 1 is around T0. This is T0 minus n to the 1 over 3 minus delta, etc. So I'm going to estimate, and the dominant contribution is going to come from here. Then in this region, one can approximate the sum by a Gaussian integral to get the result that we showed actually in the statement of the theorem. And then one has to show that the terms that come from the other ranges and that come from the other pole terms that were inside these AMNs, they are all subdominant. And this can be done in a couple of pages, basically. Okay, so now I know the asymptotic behavior of my normalization factors. Now I have the key ingredient to show tightness. And the way I do it is the same way as I did it before. I compute lower bounds on the ball volumes, and then I take the limits n goes to infinity, m goes to infinity, I take epsilon to 0, and then I rewind this process to show tightness by choosing n large enough, m large enough, and then choosing a large enough subset of trees of height r. Okay, I just want to draw, no, maybe it's good to draw your attention in the next page. And the unique, and the limits, if I call these limits of the right-hand side by psi of T0 now, one can again show that T0 is a finite tree of height R. If I take this sum of psi T0s, they also add up to 1. And these are actually the ball volumes themselves, so these are what these psi of T0s are. So let's look at this expression now in a minute, and let's compare it to what we had for mu smaller than 0. In the case mu smaller than 0, we had a k factor at the beginning, which told us to choose one branch, one top vertex to graft the infinite tree on top. Now I don't have a k factor, but I have this combinatorial factor here, which tells me to choose r of these k vertices, which says that these are going to be the vertices on top of which I'm going to attach, on top of which there are going to be grafted infinite trees, and the rest are again going to be independently distributed, and they are going to be critical Galton-Watson trees. And we're going to analyze the properties of this measure in detail in a moment, so I'm not going to say about it more. Okay, so now we know the existence of local limit also for the case mu greater than 0. So we suppressed these trees and we found a probability measure. We showed that if we look at the weak limit of these finite size height weighted measures, we get a probability measure that is supported on the set of infinite trees. But now the interesting part is to look how these measures look like, how these what is the law for their distribution. Okay, so let me give a little bit more preliminaries for that I'm going to need. I define the mu scaled simplex, by which I mean that it is the sequence of mu1 to mu n of these real numbers that are greater than 0, such that they add up to mu. And I denote the uniform probability measure on the simplex by omega. And I claim that this object that we see here, these mu's, are the probability measures that we showed to exist just in one slide ago. But these mu k's are now governed by the law of this uniform probability measure on the simplex. And this is a probability measure on t to the n. This can be shown, I mean, it's not a priori true that this is a probability measure on Tn, but it can be shown by a simple application of Kara-Theodoris extension theorem. Okay, and let me denote the critical Biennemi-Galton-Watson measure that is given by this expression here by rho. Okay, so this is the Biennemi-Galton-Watson this is the branching process that has the offspring probabilities given as, I think, 2 to the minus n plus 1. Okay. And these are critical Biennemi-Galton-Watson trees. So here comes the main theorem for the decomposition of the measure. Once I restrict the measure on the ball of radius 1 over r around T0, where T0 is a finite tree of height r, which has k vertices at maximum height, at maximal height, which is r, I can decompose the measure as follows. So let's take a moment again to look at this expression here. Okay, let's forget about these prefactors. They are associated with the base tree. This tells me to choose a subset of the vertices at maximal height such that the subset is not empty. So let's illustrate it. So I have now 6 of them here. Let's say I choose these 3. On top of the vertices that are not in the subset that I choose, I'm going to attach finite planar trees that are distributed according to this critical Biennemi-Galton-Watson measure. So these are going to be the finite trees. Whereas the other branches, there are going to be infinite trees that I will attach that are distributed according to this measure nu mu, but such that these mu i's are now distributed according to the probability measure on the simplex. So basically what they do is that these are independently distributed finite trees, but the other trees that are going to be grafted here, they have a joint distribution. They are not independently distributed. And the way that we prove this, we just show that both sides of this equation agree on this product of balls, because we know that we can characterize these measures by their value on balls. Okay. So a couple of last things that I want to mention about this probability measure. Now that I have remembered that I had this map from T infinite from the set of infinite trees to the set of infinite trees, and the image was what I called spine trees, which were the trees that are the trees that have only infinite type vertices. Then, and this was a Borel measurable map, so I can now consider the push forward measure on the set of spine trees. And if I look at this push forward measure, I can actually also try to understand how this push forward measure looks like. So this is a measure that is concentrated, that is supported on TS, and it has these two properties that are given here as 1 and 2. So the volume of the spine balls, these are the balls around the spine trees. So T0S is any finite tree of height r with r leaves, and all of the leaves are at maximal height. And the value of the push forward measure on this ball is given by this expression here, which, as you can see, only depends on r and not on the details of the base tree, which means that the random variables dr ts, which gives the number of vertices at height r, they actually constitute a Markov process. And we're going to look a bit closer into that in a moment. And if I look at the measure of the pre-image of these spine balls in the with respect to the full measure, it says that I have the critical Biennemi-Galton-Watson trees that I have to graft on every vertex below the vertices at maximal height in each sector around that vertex. Whereas the trees, the infinite trees that I'm going to graft on maximal vertices, they have the joint distribution that we talked about a slide ago. And I'm going to show you a picture, which I was very proud of until I came and see the slides and pictures of the people. So this is how it looks like. These are the infinite branches that have this joint distribution. And they have, let's say, mu1, mu2, mu3, mu4. And we know that these have to add up to mu. And this is, and they share it according to this uniform measure on the simplex. And these are the critical Biennemi-Galton-Watson trees that are independently distributed. So what we basically have is we have a backbone that consists only of infinite type vertices that are elements of these spine trees, TS. And then we have critical Galton-Watson trees that spring out from the inner vertices, from all the vertices on this backbone, and they can spring from inside each sector around every vertex on my tree. And I have one last thing that I want to say before the end of the slides. And as I will have time, I will also mention another result for another height function. So these random variables dr, ts, they constitute a random Volcom positive integer with Poisson distributed increments, which is given here. And these random variables themselves, with respect to the push forward measure, are also Poisson distributed with mean r minus 1 times mu. And now that we have more or less the full characterization of the push forward measure and of the full measure as well, we can try to compute the Hausdorff dimension that is associated with them. And it turns out that the Hausdorff dimension of the push forward measure is equal to 2, because this is quadratic in R. And the Hausdorff dimension of the full measure turns out to be 3, which is due to the critical trees that I attach on the vertices. And these results are also true for almost surely case, whose proof is much more complicated than the proof for this, which just follows as a corollary, and they are given in the appendix of the preprint. Okay, basically I said very fast everything that I wanted to say about this paper, but now I have a couple of minutes. I would like to maybe say one more thing. Do I have time, or do you prefer that I finish? Okay. All right. Okay. Should I write on the blackboard? Let me write on the blackboard so that I happen to use all the tools. Okay. You want me to stop share?
Yes.
Okay, I can also maybe. Okay. Okay. So what we did so far was maybe I should have written on the iPad. Sorry. It was a height function that was exponential in height. So I was looking at e to the minus mu ht. And one can, of course, ask, what if I start with a different height function? Does the local limit exist in a different choice if I choose a different height function? And if it does, what are its properties? And one can also look to the power-like case, where h is again the height of a tree and alpha is a real parameter. And this case turns out to be interesting for a different reason. That if one again writes one can again write these is it, n alphas, where is it, n alphas are given some. One can again look at these finite size height weighted probability measures, and then one can show that these converge to a probability measure that is supported on T to nu, but independent of the value of alpha, this measure is uniform infinite planar tree. Although the critical behavior of the generating function changes. For alpha smaller than 1, one has a finite. The generating function is finite at the critical point. At alpha is equal to 1, it has a logarithmic divergence. And for alpha greater than 1, it has a power-like divergence. And also the asymptotic behavior of these coefficients here, they change. They are not as in the case of uniform infinite planar tree, but the local limit doesn't change. So this basically says that in case of this height coupling, if I couple them to their height in an exponential manner, it is strong enough to change the local limit, whereas in the power-like case, although the behavior of the generating function changes, this coupling is not strong enough to change the local limit somehow. I don't exactly know why. And okay, maybe let me tell what kind of perspectives this kind of gives. I mean, the first thing, of course, that comes into one's mind is what kind of scaling limits, especially in the case of mu greater than 0, where I suppressed these trees, and I had the Hausdorff dimension of the full measure equal to 3. I don't know what kind of approach one should use to compute the scaling limits in this case because of this non-local nature of this coupling. I don't know. And of course, there is the question of what if I use other height functions, height-dependent functions? Would they lead to different local limits, or would they lead to scaling limits that are different than the ones that we know? And by using, for example, because this problem had the motivation from a model, a statistical mechanical model that we were studying on the causal triangulations of two-dimensional causal triangulations of the disk, where we encounter these things naturally. So one can ask for this measure in case of mu greater than 0. Could one find a statistical mechanical model that naturally gives rise to this kind of local limit, which may be some path counting from on CDTs, but I don't know yet. So I think this was it. Thank you very much.
Thanks a lot for this beautiful talk. Questions, remarks?
I can talk very loudly.
No, but for Zoom it won't be loud enough.
Hi. Hello. You mentioned scaling limits. Do you know anything about like the typical height or diameter? Or?
Yeah, I mean the typical height should be, for the mu greater than 0 case, the typical height of the average height of the finite trees should be around n to the 1/3, and this was what we used for the saddle point approximation. The width, I don't know, but it shouldn't be hard to compute because we know the distribution of the number of vertices of infinite type, and we know that all the other branches, they are critical Galton-Mollson trees, which we know to be critical, whose average, so it will have, we can calculate also the average value of the vertices at a certain height. So the average width should be computable pretty easily, and the average height, we know it is n to the 1/3. Yeah. Was there anything else that I missed? Okay.
And in front of the n to the 1/3, what do you get? Constant or a random variable?
It's a constant.
Constant?
Yeah. A constant that depends on mu.
Yeah. If there are no other questions, I have a couple of questions. So, have you tried to analyze this process as well with the random walk point of view? Because you've got random walk. Say if you condition on the height, it's just a random walk condition and not going above a certain height, which would scale to Brownian motion condition to be in a strip and so on.
No, we haven't tried. Also, I didn't have much time, to be honest, to think about different things. But no, but it's a good point. I mean, I will think about it.
And have you tried the stable case as well, where the offspring distribution has a heavy tail?
No. No, but what do you mean? In this case, we don't analyze it in terms of offspring distribution, because it's not really possible to write it as a product over offspring distributions. But maybe you mean for these independently distributed trees that are to be connected on the backbone.
I mean, the very definition of the model, you started with plane trees, which corresponds to geometric distribution, but you can ask for Galton-Watson tree, say...
together with the height coupling again.
Yes, yes.
Yes, no, we didn't try we didn't try it for any other branching offspring distribution, no.
No other questions? Let me just check on Zoom. No? Then we can thank you again and all the speakers of this afternoon.